Hi everyone, I'm Ellen Bissett.
I'm Selena Hernandez.
I'm Todd Leach.
I'm Mary Moyer.
I'm Judith Torres, and we're here today to present a fret-based biosensor that detects concentrations of progesterone in milk. The dairy industry is profitable and must meet very high levels of demand. In the US, there are 9 million cows and 26 billion gallons of milk are produced annually. Most farms are family-owned and make less than $50,000 a year. They must maintain peak productivity through herd management, which ensures a constant number of cows are lactating. Over the 21 days of a cow's estrous cycle, progesterone and estrogen levels fluctuate. Cows ovulate on the first day of their cycle for about 5 to 30 hours. If this fertility window is missed, farmers must wait 21 days before reattempting insemination. Studies show that $1 to $3 per cow is lost for each day it is not pregnant and lactating.
Current common methods of pregnancy detection in cattle include rectal palpation, ultrasonography, and chemical tests. Rectal palpation is the most common because of its high accuracy and low cost. Ultrasonography and chemical tests are expensive and inefficient for large dairy farms. Chemical tests can be used earliest at 20 days post-breeding, but the results must be analyzed in a lab, which adds time. None of these tests can provide results earlier than 25 days post-breeding. A better method of fertility and pregnancy detection will allow the farmer to know the pregnancy status of the cow or their stage in the estrous cycle without having to wait on results. The primary issue with current hormone tests is the lack of specificity, especially at low analyte concentrations. Studies have found that the presence of multiple analytes have caused inaccurate results. Our device would ideally have high specificity, fret-based response, a library of mutant proteins, and a broad range of applications.
Our solution is a fret-based biosensor. To create the biosensor, we used a transcription factor that naturally binds DNA and attached a fluorophore to both molecules. The two fluorophores excite at slightly different wavelengths. When progesterone is present, the transcription factor unbinds the DNA and binds to progesterone. When light is shown on these components, the fluorophore on the transcription factor is excited. When the progesterone is not present, the two fluorophores are close enough that energy transfer can occur, and the light emitted is the emission wavelength of the DNA fluorophore. When progesterone is present, the fluorophores are not close enough for energy transfer to occur, and light is emitted at the emission wavelength of the transcription factor fluorophore. Based on the wavelength and intensity of light emitted, the amount of progesterone can be determined.
The one major barrier to this sensor is caused by the lipids in milk. The progesterone resides in the water content of the milk, and the transcription factor primarily binds to lipids, so the probability of the two coming together is low. Due to this, a rapid and compact method of steroid extraction from milk is necessary. Using a commercially available column chromatography microsphere called AmberLight XAD2, the milk can pass through the column and the lipids will flow through, while withholding the majority of the steroids. The beads in the column are microspheres designed with adsorbate molecules that bind more strongly to hydrophobic particles, and the steroids are significantly more hydrophobic than lipids. After the lipids have passed through the column, the steroids can be eluted into the sensor portion of the device for measurement.
So what does this mean for both the dairy industry and the scientific community? Well, our biosensor can provide dairy farmers with increased independence and decreased overhead by allowing them to track their cattle's fertility cycles and pregnancy status without the need for a specialized veterinarian. This will allow farmers to maximize their production and provide better, more sustainable care for their herd. Further studies into directed evolution can also lead to the development of detection pathways for a number of crucial analytes, including insulin and cholesterol in human samples. The mutation of proteins using the methods and we have researched and utilized can potentially lead to the exponential growth in the non-invasive biosensor market. Thank you for your time, and here are some of our references.